so chapter 3 continues on with derivatives. We start applying ideas for derivatives. We've done that already with related rates, but we'll do more of that. We'll look at some things like work and all those kind of fun things later on in the chapter. But we're going to start with some pretty basic stuff. This basic stuff we've talked about already, but we need to go over it mainly to get the terminology under control. Okay, so we're going to talk about something called extrema. And I'll tell you what the extrema is. We're going to look at what relative extrema are versus absolute extrema. We're going to find the extrema if we get to it, and then for the next thing, we're going to all do it together so it sounds really cool on the recording. You should be able to snap your fingers. Can anybody not snap their fingers? No? You got like a silencer on that? You can. There you got it. Excellent. Okay, so let's start with this function. It happens to be x cubed minus 2x. It doesn't matter what the function is. But if I look at that function, what's the smallest point? What's the lowest point on that function? It seems like a silly question, but that's what I'm asking you. Negative? Infinity. Nope. It's a point.
Negative 1.5.
Negative 1.5, correct. Okay, so there's two things I'm going to ask you. What's the minimum and what's the minimum value? So the minimum is the x value where that happens. So in this case, it would be like negative 1.6. Okay, so that's the x value. The minimum value would be negative 1.5, the y value. Okay, any problems there? Pretty simple. Good. What's the maximum value? What's the largest value of the function? Infinity. Can you ever get to infinity? Can you get really close? Yeah, but we can never get to that. So from this point on, for the most part, what we're going to do now is not consider infinity a number anymore. So the answer to where the maximum value is would be it doesn't have one. I can never get to that maximum value. Another way to think about it is, what if that wasn't a solid dot? What if it was an open circle? Could I get to that value? I could get really close, but I could never quite get to that value, so therefore it would never have a minimum. Okay, so you have to be able to find a numerical value in order for it to be a minimum. Okay. Those things we just talked about are what's called absolute, and I'll go through this in some later slides. I'm just giving you an overview with this picture. Those are called absolute maxes and mins. Absolute maxima and minima. The biggest value, the smallest value. But what if I restrict the picture? What if I only look at values in this little box here? Is there a maximum in that box? Yeah. Where is it? Is that the value or is that the x or the y value you're giving me? Wait. Hold on. Let's just, Michelle, come here. Put a dot where the largest value of that function is. All right, good. Are we all on the same page? Yeah. We're talking about the same location, right? So whether it's, thank you. You can stick it on there and then. We're talking about the same location. So that would be a maximum just in that little window. And I can continue to shrink that window. And if I continue to shrink it around this dot that Michelle made, eventually we would just get smaller and smaller, but we'd still be talking about that point. That point, by the way, is what's called a relative max. It's a small chunk of the graph, and then hopefully you understand we would have a minimum down there, which would be the valley there. Okay? And that's what we're going to do. So it would be nice if we just had pictures where we just circle things and that would be it, but it's not going to be that easy. That dot that Michelle made, though, the x value looks like it's about, what, 0.7, 0.8 maybe? And the y value looks like it's 1 point something or another, 1.1 maybe? Do you think that maybe 1.1 is good enough in a calculus class? No? How can we find that point exactly? Say what? Number one, we could use a calculator. Go ahead, graph it. Graph it and tell me where that point that Michelle drew is. remember, you can't trace because we want an exact value. You gotta figure out some other way to do it. Now, I'm guessing you probably did this with parabolas last year in pre-calc. So it seems that many of you know how to use the max function on the calculator, yes? Okay. Suppose it's on a non-calculator portion of the test, because again, there's half of the test is non-calculator. How could you find that point? What's special about that point? Vertex of what? That's not a parabola, it's a cubic.
If you're just looking at that box though, you guys can find a parabola.
You can use exact.
I'm sorry, you could use what?
X value? Within X value?
How would you find the x value though? No guessing, this is calculus. What's special about that point?
Oh yeah.
It's a turning point. What does that mean? Who said that, by the way? What does that mean?
Like, to the left of the point, the graph is like increasing.
Uh-huh.
To the right, it's decreasing.
Okay.
At that point, it's not really doing either.
Okay. Neither. That is 100% true, but you still didn't answer my question. How do I find where that point happens? Actually,
If you take the derivative of it, the derivative is 0 there.
why?
Because there's no slope.
Why?
Because it's at a point.
Either increasing or decreasing, so it is
Your answer is correct. I don't know if your explanation is going to do it for everybody. So he said, take the derivative, set it equal to 0, and solve for that point.
Yeah.
Agree or disagree?
Agree.
Why? Why would that work? Why is the slope of the tangent line 0?
It's horizontal.
Ah, it's horizontal. How long were you keeping that in? And the same is true in the other window. Okay, so go ahead, find those 2 points. I'll wait. Exact values. Okay, not the decimal value you got from your calculator. Tell me the exact values for those 2 points. Harmon, where's it happen? No, just give me the x value. You have it right in front of you.
okay.
Yeah.
Plus or minus the square root of 2/3.
Beautiful. Plus or minus the square root of 2/3. two answers, because we have a max over here, we have a min over here. Suppose you didn't have the picture. Suppose it was a function that you had no idea what it looks like, but you did all this and you figured out, hey, here are some points that it's a max or a min. How would you figure out if it was a max or a min? What in the problem indicates that this is the high point in that area and this is the low point in that area? Any ideas? Yeah. Okay, look at the leading coefficient. The sign or the value? The sign of the leading coefficient, one possibility. Any other ideas? No? Okay. And that's fine, because we're going to get to that later. And I'll show you some methods to organize that that'll make it real easy. Okay, so now that's pretty much the entire lesson. Now what I need to do is show you the calculus involved in that. And show you a couple situations where this works. So here's the fancy calculus bee. You already know this though, but this is how you would find it in a textbook, which is where this came from. F of c is a minimum of f on I, where I is some interval, if f of c is less than all the rest of the function, which is exactly what you told me earlier. It's going to be a minimum if it's the lowest point on the graph. If it's smaller than every other point on the graph, it's got to be a minimum. The opposite is true for maximum. It's going to be a maximum if it's the biggest value than any other point on the graph. If we're talking about the entire graph, that's called an absolute extrema, sometimes called a global extrema. Almost every time I refer to it, I'll call it an absolute. I never use global. However, one of my colleagues, you know who that is? Grassy. He likes to throw in global every once in a while, but it means the same thing. Where's the biggest point on the whole graph? Where's the smallest point on the whole graph? That's not the window business that we talk about. That's coming up in a second. Whole graph, absolute graph, global, blah, blah, blah. Okay, great. We knew that already. Okay, so now we talk about relative. Relative extrema are just looking at small windows, also known as local extrema. I seldomly use local, but we know who does use local. They'll show up on a quiz somewhere. But looking at that little window there, what's the biggest value and what's the smallest value? Hills and valleys, peaks and valleys. And we're going to talk about how to find those things coming up. Not relevant. Okay, so let's talk about these two. I've got two functions here. Let's focus on A. I would like to know what happens if you take the derivative of that function in A and you plug in the point 32. What will you get for an answer? Do that, please. Take the derivative of f and plug in 32 and see what you get for an answer. And there's a couple different ways to take a derivative, so this will be good practice for you. This derivative in particular.
what that number is, thank you. What does that mean?
What's it?
Graph the function, not the derivative.
No, we vertex. So give me a picture of what it would look like if it wasn't a maximum. That was your function. Okay. Are those all maxes and then some?
Oh, if you restrict it to small.
But, no, it's not, so it does have to. No, I said it could not be, just what I said.
Okay.
It could be not a maximum.
Oh, so where on that picture is your value that is not
Here it is. Let's put a big picture. This is my it's supposed to be zero.
Well, what about for a relative? In any small portion of the graph, is that maximum?
Yes. It is a maximum.
It has to be.
Yes. It is called. Yes. It has to be.
All right, what do we got?
Zero.
0. Anybody else? 0. Whoa. No. Okay, hold on. Maybe we should. Maybe I should solve this just to be sure. You're supposed to get 0, so we'll see. If I was doing this, I'd put the 9 out in front and just leave it there because it's not bothering anybody. And then you could do quotient rule. So x to the third squared, x to the third up on top, times 2x, minus big honk in parentheses, x squared minus 3 times 3x squared. Leave the 9 out in front for a second. Plug in 3, I get 27 times 6 minus 6 times 27 all over some big honking number. What's 27 times 6 minus 6 times 27? 0. Okay. So what does that mean? It never hits x. What?
A slope of the tangent.
Okay, so the slope of the tangent line is 0. So what does that mean about the graph? It's either a max or a min. Does it have to be? Graph that on your calculator, see what it looks like. I think you graphed it wrong. It should look like this. It should look like this. It should look like this. It should, there you go. There's more to it, but that's what the graph around the point we're talking about. So when you were solving that, I was over there talking to Tom, and Tom got the fact that it was equal to 0, and he said to me, well, then it's got to be a max or a min. And I asked him, does it have to be a max or a min? What do you think? You still want to argue yes?
Yeah.
So it's either got to be a peak or a valley.
Yes.
Okay. How do we check? Well, obviously we graphed it. We know that it's a relative maximum. It's the highest point in that little region of the graph. However, if you look at your whole picture, it's not the highest point on the whole graph. It's not an absolute max. It's a relative max. But we still haven't addressed the issue of, other than graphing it, how do I know that that's the highest point on the graph? So in order to address that issue, we're going to start by looking at how to find an absolute max. So instead of focusing on relative max and mins like we just did, I want to focus on absolute values, and that'll help us narrow it down to relative. Okay. So we're going to jump up to this guy. That point that you had, 3, 2, we're actually going to end up solving those problems backwards. We're going to take derivatives, set them equal to 0, and solve for where that happens. In that last example, I worked it backwards. I told you where it would happen. I just wanted you to get 0. Those locations are what's called critical numbers. And they're called critical numbers because they're really important, and you're going to do this a lot. You're going to get sick of finding critical numbers because that becomes the gist of what we do in Chapter 3. And that can happen in two different situations. It can happen when the tangent line is equal to 0, or where the function is non-differentiable. And if you get to this definition here, you see that both of those are addressed. People forget about the non-differentiable part. Okay, when is a function non-differentiable? When it's discontinuous, when it has a cusp, which is what that's a picture of, or when it has a corner. Most of the work we're going to do, however, is going to be when f prime of 0, or f prime of c equals 0. Where does the derivative equal 0? So I cannot tell you how many times you're going to do that process. Take the derivative, set equals 0, solve. Take the derivative, set equals 0, solve. Over and over and over again. And then what we're going to learn is what all of that means and how do we move forward. Okay. But until then, we want to talk about this. Finding an absolute value, or finding a maximum or a minimum on an absolute graph, or an absolute extreme. Where's the biggest point on the graph? Where's the smallest point on the graph? And we did that at the very beginning of the slideshow. Okay, so I gave you a picture and you told me where the high points were, where the low points were. Here are 4 steps. For those of you who like algorithms, here are 4 steps to do that. Find the critical numbers, test the critical numbers, test the endpoints. Whatever one is the biggest is the max, whatever one is the smallest is the min. It's a pretty straightforward process. Okay, you ready? Beautiful. Elliot, what's that graph look like? Any idea? You know what a quartic looks like?
Yeah, it's like a W, I know, right?
Is that W up or down? Well, it wouldn't be a W if it was down. I'm an idiot, sorry. You're saying it's a W, not a M?
It's a W.
How do you know?
It's positive. There's a
What's it?
3x to the 4.
Yeah, the leading coefficient is positive, so you're guessing it's a W. Okay, so graph that, please. Before we start doing the actual calculus involved, let's take a look at the picture and see what the picture looks like. See if we can figure out where the biggest value is and where the smallest value is. Now, what I would suggest is set your window close to -1, 2, so that you can only look at part of the graph. Because she is correct that it is a W-looking thing and it goes on to infinity, but we don't care about going on to infinity. We care -1 to 2.
Just make it. Just make it.
Is it look something like that?
Yeah.
Okay. I purposely put arrowheads on there because I wanted to show you what the whole graph looks like. But we're only going to look at from -1 to 2, which happens somewhere over here. And where's 2 here? Is it way over past the little valley? Okay. So we want to look at this part of the graph. The stuff in red. And find the maximum and the minimum. And again, these are absolutes because we're looking at the whole part of that red graph. So I need to do those 4 steps. First things first, take the derivative. Go ahead, I'll wait. Good, you should be done by now. Set that derivative equal to 0 and solve to find the critical numbers. Alright, so we got two critical numbers, 0 and 1, yes? Okay. If we had the graph, that would be great. Let's pretend we don't have the graph. 0 or 1 could be a max, 0 or 1 could be a min. How do I know if 0 is higher than 1 or if 1 is higher than 0? Say again? Plug it in. Okay, so now that you know that our critical numbers, I didn't do the math, but we know that 0 and 1, x equals 0, x equals 1 are our critical numbers. Find f of 0 and f of 1. What's f of 0? 0. What's f of 1? How much? Negative 1. Because we're talking about absolutes, we have to take two other things into account, and that is the endpoints. We already did the critical numbers, the 0 and the 1, but now we need to look at the endpoints. And so how are you going to organize this? When you're looking for absolute extrema, you want to put things into a T-chart to help organize your data. Okay, so here's the, where is it? I got it in here somewhere. Hold on. This is all, yeah, we did this already. Great, beautiful. Okay, here we go. So I threw everything into a T-chart. Mine's a little fancier probably than you would do. Negative 1 and 2 are my endpoints. 0 and 1 are my critical numbers. And then the stuff in the right column are all the y values. Which one's the biggest value? Right. At 2, when it has a value of 16. What's the smallest value? Negative 1, which happens when x equals 1. We're going to stop there today. We'll come back to this on Monday. I don't want to get too far ahead of 6th period.
What if we didn't snap our fingers? Oh, that's what we're doing.
What?
Are we snapping our fingers?
You already did.